Hello everyone, and today we are going to talk about our lecture number. Bring my pen, and I pick this pen, and here it is. So I'm going to do our lecture number 20. So today is our 20th lecture. This lecture is all about um, how to use orthogonality. This is orthogonality. So the whole concept is really neat, and it talks about many of the issues that we face when we have vectors and vector spaces. Okay, but before I go into this, let me go back to review some of the material that we had last time. हमने कुछ material review किया था, उसको देख लेते हैं. So let's talk about a three-dimensional space. So I'm talking about a three-dimensional space. I will represent it this with this R cube. So it's a three-dimensional space, and I wanted to find a basis for it. So we want to know. So let me clean it a little bit. So we wanted to find. So we want to find. We want to find the basis for it. Find the basis. So you remember from my last lecture that we talk about the basis. Okay, and this is a very unique word. Actually, it means the set of a couple of independent vectors. If you take a linear combination of those, then they will form the whole space for which that basis is defined. So we're going to find the basis for it. So let me draw a set of bases. So my set of bases is 1, 0, 0. I call it natural basis, and you can see why I'm calling it natural basis. 0, 1, 0. Let's see. Okay. And then I have another basis 0, 0, 1. So now these three vectors that I'm watching right now form the basis for my three-dimensional space. Okay. And here I am thinking of, so I put them in a set, and this becomes the basis. This kind of natural basis, if you can see that I'm putting 1 and the other two component 0, then I put 1 in the middle, another two component 0, and then I put 1 at the end and other two 0. So in some way, you can think of it that these are called standard bases. So these are standard bases for R cube. So by having a linear combination of these three, I can form a whole R cube. So how I will make a linear combination? I will just take an arbitrary constant, C1 times 1, 0, 0 plus C2 times 0, 1, 0. And then I can make plus C3 times 0, 0, 1. And if I choose C1, C2, 3, so for any choice of C1, C2, and C3. So any choice of C1 and C2, C3, if I plug in, I will make millions of vectors. So I will make millions of, let's say I pick one particular combination. So let me go with this green color, and I pick here. So I pick 2, 1, 0, 0. Then I pick, let's say 0. Then I have 0, 1, 0. Then I have, let's say 1, so 0, 0, 1. So now my choice is for C1 and C2, C3 is, okay, so my choice is 2, 0, 0. If I do this choice, what will happen? I will end up with 2, 0, 0, because this 2 has to go and multiply with each component, okay? And then I have this plus, and then 0 has to be multiplied with everybody. So this become, all components will become 0. Then this scalar 1 has to be multiplied with everybody. So I will get 0, 0, 1. And now what I will do, I will add component wise. So 2 will add to 0, then to this 0. So you can think of it. Let me do this. So let me put an arrow. So this 2, the 2 that I'm talking about, this component will only be added to this component. Okay. And then they will add to this component. So it means that component by component, I will add them. So I will end up with, from this addition, I will end up 2 here. Okay. Then I will do another addition where I will go from this 0 to this 0 and this 0. So this will become 0. Then I will add this 0. I will add to this 0 and then add to this one. And if I do this, then I will end up with 1. So my addition is, so it means that by choosing, so by choosing C1 equal to 2, my constant C2 is equal to 0 and C3 equal to 1, I got a vector 2, 0, 0 from the basis, from the linear combination of bases. Okay. Similarly, if I do another thing, I give C1 equal to 0, C2 equal to 0, and C3 equal to 1, then this will give me another linear combination, and it will give me another resultant, which will be, of course, this will be 0, then this will be 0, and I will end up with this one. So you see, if I just concentrate on what I have done basically till now, you will see that I'm getting these vectors. See, I got, this is one vector, this is another vector. So by giving different values to C1, C2, and C3, I can come up with many new vectors, and all those vectors are actually are obtained as a linear combination of my standard basis. And that's how I can fill the whole R cube. So I can fill whole three-dimensional space. I can fill the whole R cube. Okay. But now I want to hit another point. Let's go back to where we started from. We said that we have a three-dimensional space and we are trying to find the basis for it. So one of the bases was the one that we just saw. So this is our one particular basis, which we call standard basis. Okay, nice. But then we also learned one new idea last time, which was that these bases are not unique. We can have another basis. So let me clean up this code, and let's come up with a new basis. Okay, because the basis is not unique. I can have another basis, and I can fill the R cube. So let me find this new basis. So I will just use the green color and I will put a new basis. So let me define a new basis, which is 1, 1, 2. This is the basis I choose right now. Okay. Another one, because I have to have 3. 2, and now I can do one more thing, and which very nice. 2 plus 1, I can have a 3 here, then I can have if a 5 here, and then I can have so let me put here 5, and then I can put here 8, so that these are independent of the first one. So let us say these are my bases. So this is also a legitimate basis, because if I make a linear combination of these, okay, as you can see here, so if I put a linear combination of these bases, like C1 times 1, 1, 2 plus C2 times 2, 2, 5 plus C3 times 3, 5, 8, I will fill the whole space. So this will fill whole of the space. So that one will also fill the whole R cube, because these are 3 in count, and at the same time these are independent. So the only condition on the basis is, so the only condition for basis is count should be correct. Count should be same as the count should be correct. So it means if I'm talking about 3-dimensional space, I should have 3 vectors. If I'm talking about 2-dimensional space, then it should be 2. The other thing is vectors should be independent. Vectors should be independent. Okay. So if you satisfy these 2 conditions, then you can have a basis. So there could be many more bases for the same space. Not a problem at all. So the only thing that we need to be careful is that we need to really make them independent. So that's the only test we have. And okay, so now let me move towards, once we did some revision, let's just move towards our previous picture of subspaces. We said that we have subspaces associated with a given coefficient matrix. So if you give me a coefficient matrix, I should be able to find and compute its spaces. Okay, so let me write down here a matrix, and then I will try to find its subspaces and try to see something new today. Okay, so here is, and we are going into it. Okay, so here is a matrix. Okay, so keep in mind we are talking about Ax equal to b, which is a linear system of equation. Linear system of equations. So the important thing here is linearity. This is one important thing, and the other thing is not one equation. It is a system of equations. So it's more than one equation. So our aim is to find x. So given A and B, find x. So that's what we call solution. So when somebody say that I find a solution of linear system of equations, okay, then he means this, that given A and B, he was able to find x. So but there are certain conditions when we are able to find x and where we cannot find x. So there are certain conditions to be satisfied by A and B in order for us find X. In some cases, we are not able to find X, but in other cases, we are able to find X. So I will not go into the condition, but the obvious condition is that B should be inside the column space. Then there is a chance that we'll be able to find a solution. If B is not in the column space, not part of the column space, then it's not solvable. Anyway, so let's move forward towards a particular. I'll erase this. So a particular coefficient matrix. So I will just put down here a coefficient matrix, and then we will try to associate with it subspaces. As we know that there are 4 subspaces that we can form by just having A. So here the A is given to me, and I am supposed to find. Okay, so here is this A, and the A is this 1, 2, 3. Next row is 1, 2, 5. Then 2, 4, 8. You see, why I do it? Because this is 1 plus 1 is 2, 2 plus 2 is 4, and then 5 plus 10. So now you can see why I put this 2, 4, 8 as the last row. Because the last row is actually a sum of, so the last row, so I will say R3 is a sum of R1 plus R2, and you can see it very clearly here. If you add these 2 rows, you will get the 3rd row. So in other words, matrix A contains only 2 independent rows. Because 3rd row I can easily form. If I know R1, R2, I can make R3. So if a row can be made as a linear combination of the other rows, then that row is not considered to be independent. So this 3rd row is a dependent row. So let me make it more like this. So row 1 is okay. When I say okay, it means it's independent. Row 2 is okay. Why okay? Because although 1 is same as this one, 2 is same as this one, but 5 is different than 3. So this row is independent of this. But this one, no. This row is not linearly independent from the first 2 rows, because if I add these first 2 rows, I can get, so it means row 3 can be made as a linear combination of first 2 rows. Okay. Now here I will give you a concept of row vectors. So let me say, because many of the students ask me, I sometimes take the rows and make vectors out of them. Sometimes I take the columns and make vectors. So how we do this? So let me write it down. So I want to draw or extract. I will say, okay, extract row vectors from the matrix A. Now this matrix is a coefficient matrix. You should always keep that in mind. I will just go down a little bit. So I'm going to extract row vectors from this matrix. I will do just a little bit of cleaning here. Okay. I'm going to extract the rows, but I'm going to extract, and I'm going to call them row vectors. So when I call them row vector, what happened to them? Okay. Keep in mind that whenever we talk about vector, we are talking about column vector. Okay. Okay. So whenever we talk about vectors, we are talking about column vectors. So I will just go up a little bit, and now I'm going to do it. So here is my row vector. So my row vector number 1. So let me call it R1, and I put this. This become a row vector. Now this row vector is 1, 2, 3. Now see what I did. I took the first row, okay, and I put it as a column. So the moment I put it as a column, this become a row vector. Then my second row vector, R2, I will take the second row, okay, and I will put it as a column, 1, 2, 5. So when I talk about row vector, I mean this. And similarly, if I want to look into my third row vector, then it is 2. I'm taking third row, but I'm putting it as a column. So the moment I put them as a column, they become row vectors. Okay. So now here is, let me emphasize this more to make it clear now. Okay. So row vectors are always in one column format. You see this now? So this is one column format. You have, so you took the whole row, okay, and you bring it like this. Similarly, you took the second row and you make it like this. So the moment you make it like this, it will become a vector. Here it is. Okay, so this is my row vectors. So I will extract row vectors. So if I look at those row vectors, and if I take the linear combination of these row vectors, this will make a row space for me. So I'm now going to make C1 times R1, okay, plus C2 times R2 plus C3 times R3. So if I do this for all choices of C1, C2, and C3, I will make a row space. So my row space is actually all linear, my row space is all linear combination of row vectors. Now, this is what I want to emphasize here. So row space is all linear combination of row vectors. And now let me define the column space for you. So let us say I want to do column space. But for column space, I would be, now let me clean it a little bit. And I just, now I will, so I am now going to make the column space. So for column space, what I will do, I will just pick columns, but when I pick them, I have to form vectors out of them. So this is my first column, and I will make my first, so this is C1. Now I will put them as a column. I will take the second one. This is my second column. So this is my vector. So now the moment I put them in columns, these 2 to 4, although they're already in column, then they become a column vector. So this is C3. I will pick this 3, 5, 8. And if I pick this 3, 5, 8, 3, 5, 8, this will become my column vector. So these all are my column vectors. And previously, so this is my 3 column vectors. And now if I compare them with my row vectors, then you will see what I mean by it. And now I say R1, and this is my 1, 2, 3. comma R2. This is 1, 2, 5, and R3 is 2, 4, 8. So this is my R3. So now you can compare very easily. Now compare, this is a column vector. This is a second column vector, and this one is a third column vector, whereas this one is a row vector. So these are row vectors. Although they both are vectors, but one is column vector, okay, and the other one is row vectors. So these are row vectors. That's what I'm ticking with the green one. And the red ones are the column vectors. So I can make column vectors from a matrix. I can make row vectors from a matrix. It's my choice. So here is, I'm going to clean. So I can make row vectors and I can make column vectors from a given coefficient matrix. So here I can make row vectors, I can make column vectors. So we can extract row vectors as well as column vectors from a given coefficient, from a given coefficient matrix A. So from A matrix, I can make row vectors, I can make column vectors out of it. So if I take row vectors and find the linear combination of row vectors, so if I form a linear combination of row vectors, so here is linear combination. So if I make linear combination of row vectors, and I can also make a linear combination of column vectors. So if I make a linear combination of row vectors, I will end up in a row space. Okay, so let me do this. So if I do a linear combination of row vectors, I will end up into row space. So I will form a row space here. And if I do a linear combination of column vectors, then we will end up into column space. That's how you should look at it when you talk about row space and a column space. Okay, so now we are going to look into a concept of row space and null space. And we are claiming right now is that that row space and null space, these two spaces are orthogonal to each other. Okay, so last time we basically form those spaces. So let me form. So this is my row space. Okay, so this is my row space, and you know where I form it. And then this row space is actually form an intersection at the origin, just at the zero vector, with what is known as null space. Null space. So keep in mind here we have ax equal to b. So the unknown x. So from so we can think of it as A. So let's say my A is m rows into n columns. So this is the order of my A. Now what will happen in this case, the r raised to power n, so all the vectors in r raised to power n will enter into A, and the A will transform them to vectors in r raised to power m. Okay, so So for this is the situation you should think about. So if A is the order m into n, so it means x belongs to um, r raised to power n, and x is our unknown. Um, so this space that I'm talking about right now is r raised to power n. This is the space. So think about it, that this space in which this row space and null space resides. This is r raised to power n. So row space is a subspace of r raised to power n. Null space is also a subspace of r raised to power n. Now the question is, and this is a big question that we are trying to investigate today, is that, let me clean it a little bit, this, um, that all the vectors in row space are orthogonal to all the vectors in null space. So what we mean by orthogonality or saying orthogonal, actually it's a kind of fancy word for something which we know from geometry, which is perpendicular. So perpendicular means 90-degree angle. So what we are saying right now here is that orthogonal. So orthogonal actually means perpendicular, or in some way I can think of it as 90-degree angle. Okay. Before we look into this, that one subspace is orthogonal to another subspace, let us look at how two vectors can be orthogonal to each other. So let's look at the simplest problem. They say that things can be much more simpler if you look at the simple things. So let us look into the scenario under which two vectors. Now, these two vectors could be two column vectors or two row vectors. We don't care right now. What we're saying is that we just got two vectors. One vector is x and the other vector is y. These two vectors, under which conditions these two vectors are orthogonal or orthogonal. So what we are saying is that one vector will be this, let's call it x, and the other vector will be perpendicular to it. So this is the y. And the angle between them is this 90 degrees. So x and y are perpendicular. So when we say they are perpendicular, or when we say these are orthogonal, we means the dot product. So the dot product of two vectors is 0. So when the dot product of two vectors is 0, that basically means that they are orthogonal. Okay, but let me clean a little bit of space around here so that we can work a bit more independently. Okay, so when we say two vectors are dot product, but in case of vector algebra, or we can say the linear algebra, um, to look at two vectors. So you should keep in mind always that x and y both are columns. So they could be row vector or column vector, it doesn't matter, but they are in column. When we put the vectors, we put them in columns. When we say vector, it means column. So if I take the row, so in order to take the row of this vector, I have to transpose it. So I will do the transpose, so this become a row now, and then I multiply it with the column. So now x transpose is a row. So because you remember originally it was column like this, and when you did the transpose, it become a vector which become a row. And here is a y which without transpose operation is still in the column form. So when I do this X transpose Y, actually I'm trying to implement, but rather I'm implementing dot product. So X transpose Y will always give me a single number, and that single number should be 0. If that number came out to be 0, that will tell me that X and Y are both orthogonal. Okay, so the verification is that X transpose Y operation should give you 0. Similarly, we can also say that the Y transpose X, okay, in this case, Y become a row, because under the transpose operation, originally Y was a column, which become under the transpose a row. So the row times a column, again, it should be 0. So the order here doesn't matter when, as far as orthogonality is concerned. So then we can fairly easily announce that X and Y are orthogonal. So I will just clean a little bit. So in this case, X and Y are orthogonal. Okay. So now let's look at another very important theorem, or the law which you can apply, Pythagorean theorem. Pythagorean theorem. Okay, Pythagoras law. Pythagorean theorem. Okay, and this theorem applies to right angle triangles. Okay, right angled triangle. And we all know about is that hypotenuse square is equal to the base square plus the height square. So let me look at the same scenario. X and Y are orthogonal, and I'm going to put their resultant X plus Y. So the resultant will go at head to tail rule from the bottom of the first, from the tail of first to the head of the next. And now the Pythagoras theorem says that the hypotenuse distance. So for the distance, we put always a double bar. So the distance square of hypotenuse is equal to the base distance square plus the height distance square. Now, this theorem, one should keep in mind, only applies to, so I will just clean this a little bit for my, get some space here. Okay. This particular theorem is not valid for all triangles. There are some special triangles, we call them right angle triangle, and it's true only for them. So let us say we don't know the condition under which the left hand side is equal to right hand side. So this will become X plus Y transpose X plus Y. So this gives you the distance square, and then this will be equal to the, and I still don't know, so I'll put a question mark here. So X square, X norm square, which is the X distance square, so it's become X transpose X, and this is Y norm square, so Y is a vector, so it's a distance square, so Y transpose Y. Okay. And now if I open this up on the left hand side, this will become X transpose plus Y transpose, and then I will have this X plus Y. And if I multiply them together, this will give me X transpose X, this X transpose with this first one, and then this X transpose goes with the Y, so this will become X transpose Y plus Y transpose X plus Y transpose Y. That will be equal to X transpose X plus Y transpose Y. Now, if you go into this and you try to look into those, and here is a question mark. Okay. Now, X transpose Y and Y transpose X are the two things which are same, because this will give you a dot product of X with Y, and this gives you a dot product of Y transpose X. So what is dot product? Here I can say this X transpose Y is a dot product X1 Y1 plus X2 Y2 plus, let's say, 3 components. So this is actually a dot product. So I can say here that this becomes 2 times X transpose Y. and the other terms are X transpose X plus Y transpose Y. Now since this X transpose X is on the left side, the same is on, so I can cancel them up, and Y transpose can go on this one. So now what happened? So I reached to a conclusion which says, and that is really nice to look at it. And the conclusion is, let me clean this. Now the conclusion is, and it's a very nice conclusion to see, which says that 2 times X transpose Y is equal to 0. Of course, 2 cannot be 0, so we can conclude from this whole arrangement that X transpose Y is equal to 0. Now let's look into the implication of this one. So there are some effects that are generated by this. So let's look into those effects. Clean it. So when I say that X transpose Y is 0, then one situation could be that either one of them could be 0. So it's a degenerate case. So when I say X transpose Y is 0, that means either X is 0 or Y is 0. So it means either X is a 0 vector or Y is a 0 vector. So if you have a 0 vector and you try to find, and you try to take the dot product of the 0 vector, then of course every other vector will become 0. So we can conclude here that 0 vector is orthogonal to all vectors. Okay, but this is a degenerate result. We cannot get anything new from this one. 0 condition is a degenerate case. So let's look into some generate case. So for non-zero vectors X and Y. So let's say these both are non-zero. Then X transpose Y implies, 0 implies that X and Y are orthogonal. So in other words, the conclusion we draw that the Pythagoras theorem also says the same thing, that this question mark can be removed. So this question mark can be removed if X is perpendicular to Y. So if X is perpendicular to Y, and that's how I write perpendicular, the inverted bar. If X and Y are perpendicular, then this side is equal to this side, because then it will become a right angle triangle. So keep in mind that we have verified the Pythagoras theorem. And now we basically left with it, the basic question. And the basic question we were looking for is for our space. And we were saying that row space is orthogonal to the null space, and how it is. So let me look into this. And there is a very neat derivation for this one. Just you think about the definition of the null space. So what is the definition of a null space? How we find null space? So null space is A times X equal to 0. So this X that once multiplied with A gives you 0, those X form null spaces. So these X, all such vectors X form null space. So all such vectors X form null space. Now think about it. So it is a null space. Okay, so all those vectors which satisfy this matrix equation A times X equal to 0, then that X will form a null space. And now we look at it in a more generic case. This means that here is our row 1. Okay, so here this is our row 1. Then we have row 2. This is our row 2. And let's say this is our row M. So there are M rows because we have M into N. So this, and then we are multiplying it. Okay, so here we are multiplying it with X, and X is of N components. N components. So we can think of X as X1, X2, up till Xn. Okay, so that's how you think of it. Equal to, and now if I just take here zeros, how many zeros? I will have M zeros. 0, 0, 0, dot, 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 0. How many zeros I have? M zeros. Okay. So now, how this first 0 is formed? Just look at it. I will just clean this one little bit. How this first 0 is formed, and that's very interesting to look at it. How this first 0 came into being. So let me look into this first 0. So first 0 is formed because row 1 multiplied with X. So I will say row 1. Okay, I did the transpose of row 1 with the X. So row 1 transpose with X. Okay, this will give me 0, because you should keep in mind that once you make, so here, this is not just the row, this is the row vector. So I'm putting this one, arrow. So the moment you put this arrow, this row 1 does not remain as it is. It becomes, so this become like, if I can make it ROW1. So you see, this become a column now. So once you do the transpose, it become a row. So the row times the column, X, whenever you have a vector, it's always in the column format. So this is like a column. So the row times the column is 0. That's why you get this particular 0. Okay, I'm talking about right now. Here, let me do this. So this 0, I'm talking about this 0 is actually what you get here. So this is the same 0 that you got it from here. Similarly, if you do this now, row 2 vector, and you transpose it, and you did the X, you get the second 0. The second 0 is coming from here. And so on. So you will have M zeros and you will have M of these. So from here, you can see very clearly that each row, because if a row vector is a transpose with the X and give you 0, that means that the row 1, this implies, so this implies that row 1 vector is orthogonal to X vector. Now, what is X vector? X is a null space vector. Similarly, the second row implies that the row 2 vector is orthogonal to X vector. So on the same pattern, if I just go along with this pattern, and I can say very clearly, and I will just make a big claim here, that all the rows of A are orthogonal to X. So I can make a claim here. All rows of A are orthogonal to X. And now what is X? X is null space. So I can once all the rows of A are orthogonal to X, I can make a linear combination of rows of A. So C1 times R1 vector plus C2 times R2 vectors plus Cm times Rm vector. So this is a linear combination, and that's exactly what makes the row space. Now this whole transpose is with the X will give you a zero vector. So that shows that the whole row space is orthogonal to X. So the whole row space, it means everybody. That basically means everybody. So what we are saying here is that every vector in row space is orthogonal to every vector in null space. So we also use a very special name which is called orthogonal complement. So orthogonal complement. So what we are saying is that the null space is orthogonal complement to row space. So with that, I will just end up my lecture, and I hope that you understand some of the concept. If you have any question or confusion, please leave a message or a question on the YouTube, and I will hopefully answer it, okay, in a short time. Thank you very much, and we'll see you next time.